Good day, everyone. My name is Kamau. I'm a senior software engineer at Heimann Technologies, a software engineering consultancy based in Berlin. Now, in this presentation, I'd like to talk to you about a particular pain point that for sure many of us have experienced while dealing with data, and how ZIO Schema can help alleviate that pain. I'm quite thrilled to be here and share something that I'm quite passionate about. Okay, there you go. Data is a currency of our applications, right? We hear that often. The logic we implement involves merging it, transforming it, enriching it, and performing many other operations on that data. These operations bring about different challenges that need to be addressed even before we can start using that data. The problems we face when dealing with data tend to be similar, regardless of whether that data represents information on the financial, health, entertainment, or just about any other domain we can think about. And one of these problems that we face is a codec problem, right? So the encoding and decoding of data. Codec is essential because we receive data in one format and must then convert it into a different format, right? We receive data as JSON, and then we need to transform that into an ADT, say for validation. We may even receive data in CSV format, then persist that data in the database, probably in a slightly different format. While the specifics of these codecs may differ from case to case, right, depending on your use case, the overall design has very notable similarities. Right? Codecs play a crucial role in the various aspects of backend systems, microservices, data analytics, and just about any other system we build. Microservices often communicate with each other using lightweight protocols like JSON, protocol buffers. Codecs are used to serialize and deserialize data in these formats, ensuring efficient communication between microservices. Now, the choice of encoding and decoding mechanisms can greatly impact the overall performance and the responsiveness of the microservices. In data analytics, ETL processes may convert data from one format to another. Codecs can be applied here also to transform and use in these transformation processes, ensuring that we end up with the appropriate data formatted in the appropriate manner. Microservices often communicate through events, right? Also in this use case, codecs are used to facilitate the encoding and decoding of the payload, enabling real-time event handling is crucial, especially in those scenarios where you're relying on event-driven architecture for responsiveness and scalability. Now, solving the codecs problem can be quite challenging, especially when considering the solutions that involve reflection, manual coding, dynamic approaches, and many others. Data structures in real-world scenarios are complex. They're not simple. They are complex and diverse. Reflection, which allows your program to kind of examine and modify its structure, may struggle if you have complex data structures. Then manually writing code for each data structure can be time-consuming and error-prone. Reflection and dynamic solutions also introduce overhead, right? Runtime reflection, so inspecting and manipulating the structure of types as your code during execution can result in slower performance compared to static compile time solutions. Choosing to manually write your own codecs for your data types can also lead to maintenance challenges. Now, just as your code base grows and you add different additional structures, maintaining and updating those handwritten codec implementation will obviously become labor intensive and most likely prone to errors. Reflection-based or dynamic solutions tend to sacrifice type safety, right? There's no going around that. But you need type safety. Ensuring the right types are used during encoding and decoding is essential to prevent those errors during runtime. Well, two popular solutions in the Scala community when it comes to solving these codecs problems are Shapeless and Magnolia. Shapeless is designed to provide generic programming features such as generic type representation of data types, generic operations, and type-level capabilities, type-level programming capabilities. With Shapeless, you can go from an ADT to a type-safe generic data representation and back. This provides you with methods that can work generically on any type, record, or enumeration, so case class included. Magnolia, on the other hand, is used predominantly for class type derivation, right? That's why it shines. Type classes allow you to provide a set of common functionality across different data types without having to change the inheritance hierarchy of those types. You know, some common type classes include equal, show, ordering, numeric, and many others. Magnolia gives your code enough information about the structure of data types, allowing you to derive type classes for any ADT. Magnolia does not have the same set of features as Shapeless because it's not really meant for or designed for generic programming. But both Shapeless and Magnolia, in their own very unique way, allow us to get free structures, you know, like serialization and deserialization that are derived from the structure of a data type. ZIO Schema, in my opinion, adds itself brilliantly into this list with the set of tools that are designed to make our developer lives a bit easier, right? It's designed to have the simplest possible user interface to solve a selected few problems, right? Compared to the other two solutions we just mentioned, including codecs, obviously, and normal, right? By reducing the scope to very specific problems, allows it to concentrate on lowering the entry level and facilitating usage. You know, for instance, you don't even need to know type level programming or macros, right, to use ZIO Schema, as we will see in a moment. The simplest concept that is at the heart of ZIO Schema is reification of the structure of a type to a value, right? Reification occurs when you take some construct of a language that is not a value and then create a data type that models that construct so that it can be used or turned into a value. Yeah, we see this, for instance, in functional effect libraries such as ZIO that take statements and turn them into values. Optic libraries such as Monocle take the concept of a field inside a case class, for instance, and turns it into what's called lenses. Schema attempts to reify the concept of a data type structure. What does that really mean? So let's take this this type, for instance. This type called item here. The high-level definition would be a case class called item that has two fields, one called name of type string, another one called count of type int. Now, even though the data type exists, right, we have a case class called item, the concept of the structure of that data type doesn't, or at least not as a value you can interact with during runtime. ZIO Schema attempts to do that, attempts to reify that data type structure, allowing us to view that structure as a value, in fact, as a first-class value. And it does that by introducing a series of types, as you will see, Let's go through the major ones. Record. Record is a type of schema that describes the structure of case classes, okay? Case classes have names and they have fields, and a record value contains all this information. They even contain generic constructor. A record contains, I believe all records contain a generic constructor which can create instances of that class given values of each of its fields, as well as projections which can access the field values given an instance of that case class. Then you have enums. Well, that would be, so in enums in type in schema. Sorry, enums is a type of schema that describes the structure of sum types, essentially, right? That would be enum in Scala 3, or good old seal traits and final case classes in Scala 2. Collections. Collection is a type of schema that describes the structure of Scala collections. So essentially, those would be sequences, maps, or sets. Standard type is a type of schema that describes the structure of many of the common Java standard types that we know and love, right? Including unit, UUID, instance, local datetime, and all these other types you can see here. Dynamic value, on the other hand, is a generic representation of data. You can think of dynamic value as being a superset of JSON, right? It allows you to store object, array, or map-like things, as well as primitives, right? Okay, so we have those types. How do we use them? So how do we actually use your schema to decode a value? All right, let's take this map as an input example. Here we have two keys, title and authors, and their corresponding values. Then we have our domain case class called book, for which we also derive a schema. That's crucial. You know, ZIO Schema gives you the possibility of either deriving a schema automatically, like we're doing here, or manually coding one yourself. So how do you decode that incoming value? Well, there are two ways we can do that. There are two ways you can use your schema to solve this class of problems. The first approach is rather simple and solves our problem in just a few lines of code, as you will see. It involves the conversion of our input values to a ZIO Schema data structure called dynamic value. We then rely on ZIO Schema to figure out how to unpack the contents of that dynamic value to a given type. Now, this approach comes with an overhead because we need to first convert our values into this intermediate structure before converting it into the desired type. And it's also limited. It's limited to those scenarios where you know how to turn your data into a dynamic value, such that ZIO Schema can then decode that dynamic value to the desired type. So it's not always a given that you can use this scenario. The second approach is much more involved and requires writing more code in comparison to the dynamic value approach, as we'll see in a little bit. Now, this approach bypasses the intermediate layer, eliminating the overhead in CAD in approach 1. If you're building a library, okay, you're building a library handling massive amounts of events per second, and you're concerned about high-level performance, then this is the approach. The second approach is the approach you want to take. But in most other cases, the first approach will be more than sufficient. Now, in the second approach, what we do is pattern match on the provided schema and just handle every case, as we'll see in a few. Now, let's begin with the dynamic approach, dynamic value approach. Here we have a method called decode that takes an implicit schema and tries to decode the values defined in params, so our input values, into a value of type A. So the function either returns a value of type A or a failure if that's the case. The first thing we need to do is transform our input values into a dynamic value, right? Dynamic values, as we saw, is this generic representation of data. Now, how do we do that? Here we have this function called toDynamicValue, where it's simply folding over our input values and converting each value to a dynamic value. Essentially, that's all it's doing. And it gives you some leeway. So you have the choice to implement your logic to fit your various specific business requirements, right? In this, for instance, in this implementation, I have two interpretations of any given value, right? We create two interpretations of the value, and later, as we will see, pick the first one that succeeds. But you can imagine implementing this in 1,000 other ways, right? The implementation can be very specific to your use case. So once we have the dynamic value representing our input, we then we take the dynamic value representing our input and transform it to a desired type for which we have a schema, right? This is quite crucial. You can't do this if you don't have a schema for that type you want to transport or convert those values into, right? This process either fails, obviously, with a message or returns the value we need. Like noted before, here we are simply just taking the first interpretation that succeeds and going with that, right? Now you can imagine implementing this differently, right? If you have a different use case, this level of implementation allows you to just mold it to your specific use case. So here we're fine with just taking the first interpretation that works. The second approach, well, it's much more involved and requires us to write a bit more code. So we, like mentioned earlier, we essentially pattern match the incoming schema and handle all the errors. Handle all the cases. So in the first case here, we are matching a schema that represents an optional value. That schema holds another schema that represents the actual value inside the option. So we get the index schema and call decode with it, either getting a value in return or an error message if it fails. Same case here. Now, ZIO Schema provides us a way to describe the structure of a lazy value. That's what's happening here. Here we simply extract the inner schema and call decode using it, right? Record is a type of schema that describes the structure of case classes. So we call decode record here, giving it the record matched. And what does this function do? So a record gives us access to the fields of a given case class, right? And so all we need to do here is loop through the params and decode every corresponding value. In this specific implementation, we just choose to treat any missing value as an error. Again, that's I guess personal. You can implement this anyhow you like, because it's that flexible. You just imagine implementing this using your business logic. Transform is the way you take a schema of A and turn it into a schema of B, right? It's quite useful in cases where you have a schema for one data type and you want to use that schema for another data type, closely related. So those two say those two types are closely related. A good example would be, say you have a schema of string, and you want to turn that into a schema of email, where email is just a wrapper of a string, right? So that scenario transform can be quite useful. As mentioned earlier, dynamic value is a generic representation of data, somewhat like a superset of JSON. Dynamic value included in ZIO Schema because it's easier sometimes to solve a problem generically without type safety than it is to solve in type safety. ZIO Schema lets you convert case classes and enums into dynamic value and then back again, right? Producing obviously high quality errors in case of failure. In this logic, we create a record which is of type schema that describes the structure of a case class. Then for every key in params, we simply get the corresponding value and define that as a primitive of string, right? Again, this could obviously be done in multiple other ways, depending on your business logic, but you can see how it can be done here. Okay. This extended approach, this second approach, gives you more flexibility to custom tailor your logic to fit your specific needs, right? So you get to choose what you want to support and what you don't want to support. Right here, just to showcase that, I have chosen not to support collections or enums, but you could obviously provide custom code to support these cases. As developers, we are always dealing with data, right? Most of the time, it comes from different sources. It comes in different shapes. In most cases, we have to decode that data even before we can use it, which brings a whole set of problems that we need to solve that are not even related to the problem, the business logic we are trying to implement. There are multiple solutions we can implement, but ultimately we want one that solves the issue without introducing new ones, right? With ZIO Schema, you can easily create boilerplate-free codecs without having to sacrifice type safety, which is a very good thing. All right, you can find useful references, including talks, articles on the ZIO Schema GitHub page specified here. You can also find all the code I used in this presentation in my GitHub repo, also referenced in this slide. I'd like to thank ZIO for hosting such a wonderful conference, all the sponsors for making it happen, and HiveMind Technologies for being just a cool company. That's all for now, and thank you for watching.